Hello, everyone. This is Giacomo speaking, and I'm very happy to welcome you to the new event of the Hypatia series of colloquium. I'd like to start, as every time, to first of all congratulate with the speakers of the entire series and also the speaker of today. And we are, as usual, very grateful and very much looking forward to hear about the science that early career scientists are doing these days in Europe and in the world. Just to remind you to just very quickly, technically, so part of the people are attending the workshop, the event on Zoom, and you can make questions for those people. You can make questions using the chat or basically using the raise hand options. And then once the chair will give you the word, and then you can make the question yourself. This is actually very nice. Otherwise, you can also, people attending on YouTube can send the questions on the chat, or as a third approach, you can also send the question using the live the questionnaire that we have on our pages. And I posted the link on the YouTube chat, so you can use that, and we monitor all these channels in real time. So we will pass the question to the chair of the sessions. Just to remind you that these events and all other events are available on YouTube, and the links are all to the videos are also available on the Hypatia program page. And also, please go to the page of Hypatia. As for each of the talk of the speaker, there is a link to the current CV, curriculum vitae. Just click on the title of the talk and you can download the curriculum, so you can know, you can meet, virtually even bit deeper, our speakers. And please be reminded that the speakers were selected after a very competitive selection process. More than 300 applications were received for this series, and we are very proud of it. And we would like to say congratulations to the speakers, but also, of course, to say to everyone who participated that you should be proud and happy, and this will be done again. So don't worry if you didn't get the chance this time, but it will be happening again in the future. Finally, I would like to thank the two chairs of today. He's Lucas and Dominika. They are a fellow and a student of ESO. As usual, our fellows and students, they are helping us in chairing the session. This is also very appreciated, and very nice to see these young generation of people leading all of this. So thank you very much. And in fact, now I'll give the word to Lucas, who is going to make the first introduction. Thank you very much again, and enjoy the event.
Thank you, Giacomo. Hello and welcome to ESO Hypatia Colloquium. And my name is Łukasz Tychoniec, and I am an ESO fellow. And together with me will be chairing this session Dominika Eitrich, who is a PhD student at ESO, and will be your host today. And on today's agenda, we have two very exciting talks. And the first one is going to be given by Karolina Kubiak, who is currently a researcher at CENTRA at the University of Lisbon in Portugal, and she obtained her PhD in 2019 studying population of stars in the Orion belt. And her research spans across galactic star formation to the young stars and young brown dwarfs. And actually today, she will be giving a presentation on her work on environment and what impact does it have on formation of stars and brown dwarfs. So Karolina, you can share the screen now, and the floor is yours.
Okay, I will also unmute myself. Hello, everyone. First of all, thank you for giving me the opportunity to share my work with the community. Thank you for the nice introduction. And yes, I'm gonna try to summarize a little bit how the environments of different star-forming regions can impact the formation of very low mass object and the brown dwarfs. This work is done mostly in Lisbon, in Portugal, and I will, as my main project is LCW38, I will focus on the results from this, but also try to summarize this, what the group is doing in general. Oops. Oh, here. So briefly, what I'm going to talk about is what are the brown dwarfs, because I think it's the first talk about brown dwarfs in the Hypatia colloquium. So it would be nice to actually get familiar what kind of object I'm talking about. I will summarize a little bit what the current formation scenarios are, so a little bit of how to cook a brownies. and then we'll present the results of what's the impact of the environment in some observables. What is the impact of environment on some of the observables concerning brown dwarfs and low mass stars, and in the end presenting my current work. So starting from the sorry, I will try to move it. So what are the brown dwarfs? Brown dwarfs are in general very low mass objects that do not have enough mass to have a stable hydrogen fusion in the centers. So they do not sustain hydrogen fusion, which means that they, through the lifetime of the brown dwarf, they are constantly cooling. It is the gravitational cooling. It's not the nuclear fusion in the center. So as this means in general, they will never reach the main sequence phase. They are always below it. They are always trying to get there, but never reach it. They are very abundant in our galaxy. There's plenty of them, but they are very faint. Therefore, they are very hard to find. And technically, the only way to confirm something is a brown dwarf or not is obtaining the spectroscopy of it. And we know the spectroscopy is very time consuming, so it's not so easy to confirm most of them. As a definition of what the brown dwarf is, we use the mass range for them, saying everything that is below 75 Jupiter masses, so 0.7 solar masses, which is the limit for hydrogen burning, it's a brown dwarf. And that's an upper limit for the brown dwarf masses. In case of the lower limit for their masses, it's not such a clear definition. Classically, in the literature, we consider the deuterium burning limit as a limit for the lower mass for brown dwarfs, which is the 13 Jupiter masses. But we are recently finding more and more objects that are free floating, so they are not associated with any star or any other brown dwarf, so they are not the companions that are below this limit. And there is a very huge, it's a huge question where they came from. So as we can see here on a plot, it's a evolution of temperature with age for different type of object. With the blue lines, we have the object that sustain hydrogen fusion, so stars. With blue are what we call the brown dwarfs, and the red regime is the regime for planets. So we immediately see brown dwarfs are somewhere in between, but what we can see, the tracks are really dense packed, so it's hard to distinguish between objects. And what is then happening, if we follow one of the track, we see the brown dwarf can change not only temperature with age, but also it's changing the spectral types. The upper part is the limit for the M dwarfs, or the stars or object with the M dwarf type. Then we have brown dwarfs with the L type and the brown dwarfs with the T type, and this change with evolution. So for the brown dwarfs, we do have the evolution with time of the spectral type. Sorry, too fast. So in general, we have 4 spectral types for brown dwarfs right now, which is M, L, T, and Y. Going with the lower temperatures. And as we see here on the very brief graph, there is a huge mass age degeneracy. In general, it's a luminosity mass age degeneracy. For different ages, the object with the different spectral types will have a different mass regime. Okay, so like I said, brown dwarfs occupy the space in temperature level between planets and stars, but they also share properties both from the stellar and from the planetary regime. So in case of the properties similar to the stars, they are self-luminous, they can host the planet, they have disks and outflows, they have similar mass distribution, they have similar properties in case of multiplicity. When we find them in cluster, they share the kinematics and the spatial properties of the stars in the cluster. In case of the planetary properties, so properties shared with planets, they have very cool atmospheres, similar to giant planet atmosphere. The similar features can be found in spectra. But they also have a similar radiuses. So each of brown dwarfs, technically within the factor of 2, will have the same radiuses, which is not the case for stars. So how to make brown dwarfs? I will try to summarize very briefly most common scenarios of how to form the brown dwarf. So they can be formed exactly like stars. So by the turbulent fragmentation of molecular cloud, it just requires a little bit less mass and forms exactly in the same way. And that has been summarized and described by Padoan and Nudlon in 2004. They also can be created as companions by the disk instability by the disk instabilities and turbulation and then ejection from the pre-stellar disk. And that has been presented in stamatelas. So those are two different scenarios. One creates brown dwarfs as in the star-like way. The other one creates brown dwarfs a little bit like planets. Then there is yet another thing that can, in general, create brown dwarfs, which is just the stopping the accretion. So the embryos or pre-stellar embryos we just stop it accretion. So we remove the gas reservoir from around it. Therefore, we'll never exceed mass enough to start a hydrogen fusion. And it can be done just by the ejection from the molecular cloud in the creation phase. And then the object cannot accrete more mass, so will never reach the mass regime enough to be a star. Or it can be due to the presence of OB stars and the UV radiation from massive stars that will also blow up the envelope, and therefore the end of the story is the same. The object is not reaching enough mass to become a star in the future. So those are in general 4 different scenarios for how to create brown dwarfs. Of course, the details of the scenarios are much more complex than I'm presenting here, but there is not enough time. So in general, what we think today about how the brown dwarfs can be formed is that they should form as a star, at least in the mass regime up to 5 to 10 Jupiter masses. We know that from the studies of nearby star-forming regions, but it's not. This result does not exclude other scenarios. We just don't know how big role they played in the overall population of brown dwarfs. There is still plenty of questions to be addressed. One of them, few of them that I'm presenting here, is how does the initial mass function, one of the most studied observables for the star-forming region and cluster, how far does it extend into the regime of very low mass stars and brown dwarfs without changing significantly its shape? And how do the brown dwarfs form? Do they mostly form as a star or as a planet? And the one that interests me personally the most is the environment. What's the role of environment in the creation of those objects? Because all of those scenarios predict some observables that we can study. The IMF, the multiplicity, the spatial, and the kinematics of those objects. So the environment should play a role. The stellar density, the gas density, and the presence of massive stars should play some kind of role in those scenarios. So they should have an impact on observables like IMF or the star to brown dwarf ratios. Okay, so many studies have been done, and I would like to summarize here a little bit one of the large projects, which was the SONIC project. It is the substellar object in nearby clusters, where the SONIC group was investigating brown dwarfs in 5 nearby star-forming regions. And so I will mostly refer to the results from Chameleon-1, which is very rich in YSO star-forming region, but it's not so compact. What the SONIC group did, what they have as a goal, was to obtain a deep IMF, so go as low as they can in case of the masses to the very low mass object, but in the consistent way to be able to compare the result in a fair way. So they did it by using deep optical and near-infrared photometry, and then follow up with the spectroscopy. So in the end, they confirmed around 100 new brown dwarfs in those 5 star-forming regions. But the main result they obtained was that the IMF in the low end, so the end of brown dwarfs and very low mass object in nearby star-forming regions is universal, with the power law form of the slope between 0.6 to 1. Of course, the range is still large, but it's mostly due to the uncertainties of our observation. And the star to brown dwarfs ratio they obtained in this range, in these regions, was 2 to 5. Okay. And what we are doing now, since star-forming regions around in the solar neighborhood around our sun mostly have the same properties. They are not very dense. The only star-forming region having massive stars is Orion. So there is not much to test in case of the environment. So for that, we have to move, unfortunately, a little bit farther. So we pick up 3 star-forming regions, RCW38, RCW36, and NGC2244, to study differences in density of the stars, density of the gas, and the presence of OB stars. So as we can see, the difference in environment are a little bit bigger, if I can say it like that, for those regions. So first of all, the RCW38 that I will present later in a more detailed way, it's 100 times denser than Chameleon-1. So we are saying Chameleon-1 is rich in YSO, so here we are dealing with 100 times more objects. And it's also rich in massive stars. So we have plenty of OB stars, therefore plenty of UV radiation that can help us evaporate the envelopes from the embryos from the stellar embryos. Then we have RCW36, where it has a similar density to 1C. So we have direct comparison in case of the stellar density, but it has only few OB stars, actually B stars. And then we have NGC2244, which has a similar density to Chameleon-1, but an rich environment in massive stars. So we hope by investigating those 3 different star-forming regions, we will be able to say something about the differences of environment, or at least do they play a significant role or not. Personally, my object to study is RCW38, so a little bit about it. So it's at the distance of 1.7 kiloparsecs, so unfortunately we can forget about any spectroscopic confirmation of a selected object, but it's one of the densest and one of the most massive clusters within 4 parsecs from the sun. So I think we will not find any other such a violent environment for creation of low mass stars. It's as twice dense as Orion, and the order magnitude of the denser than the rest of the nearby star forming region. And it hosts dozens of B stars, which actually can be seen in this beautiful image. The image was taken by Hawkeye Graal at the VLT. So comparing what I did recently to the previous studies, in 2017 there was a paper by Cora using NACO data for the core of the cluster. I will get to the size of the cluster in a second. But the field of view was 54 to 54 arc seconds, centered at the massive binary star in the center of the cluster. And the data have been obtained in H and K S-band, and then archival data from J-band was also added. What they found as an initial mass function was segmental power law of slope 0.4 and 1.5 with the uncertainties. And the star to brown dwarf ratio was 2.1, which is, as we remember, for star-forming regions in solar vicinity, it was 2 to 5. The to make a fair comparison, we need to know the ranges of where we take the brown dwarfs and the stars from. So it's everything below 1 solar mass due to the completeness of the studies. So now, that's the previous study, and that's the image we have right now. We have actually 64 times larger field to investigate right now. We have 20 times more object in the field that has to be, that the membership for them has to be assessed. Right now, it's the largest and deepest near-infrared survey done in RCW 38. And we have a field of view in the physical scale around almost 4 parsecs. But still, it's not the full cluster. The cluster is much, much larger. This is the surface density of YSO plot taken from Winston, where the density map has been created based on the YSO identify using Spitzer data in comparison in the Spitzer data, Tumas data, and Chandra data. They identify YSOs and create the surface density map. We are covering really nicely right now the center of the cluster. There is still some substructuring in the cluster that has to be addressed, but I think we will get a nice overview of the environment out of the Hawkeye data already. So what we did for all of the sources, after reducing the data, we created color magnitude diagrams. And on the left panel, we can see actually the H versus H minus K color magnitude diagram for the cluster, overplotted with the tracks, with the evolutionary tracks. With the red dots, I marked the sources that have a Gaia parallaxis. Of course, the foreground sequence is nicely separated, but in the bulk of the plot, we don't have a clear separation of the cluster members. So it's a combination of background, foreground, and the cluster members. Gaia is pretty shallow in this data. Majority of the sources don't have a Gaia comparison, so we really need Gaia in infrared. Average extinction to the field, it's 10 magnitude, but I'm saying it's an average extinction. Extinction is very variable in the field, and it also has to be addressed very carefully. We reddened the sources. We obtain extinction to each of them, and redden them, and then get the masses. We divide our sources into 3 groups based on the position on color diagrams. And the sources in the field A has been the mass was just obtained by the reddening source to the tracks. In the region B, we were applying also a little bit of correction for the presence of the disk. And in the field C, we were also applying a correction due to the possibility that the source can be actually a Herbig AEBE stars. After obtaining extinction and masses for all of the sources, we were trying to estimate the membership. Since we don't have any other indication of the membership, we did actually just the statistical assess how many sources we can get as a members of the cluster without pinpointing that the single source is a member or not. We were just interested in how many sources we will get. We actually used the method presented in Bonato Bika paper. So we divided the color magnitude diagrams in a grid of the certain step in magnitudes and the color. Then we assess the probability of how many sources from the control field presented here in the black can be members, and then just randomly removing from in each of the cell how many sources should run out of the cluster. So going very fast to the result, the initial mass function is presented in the step function of 0.6 for the low mass and around 1.7 for the more massive stars. We are actually very incomplete in the range of massive stars because they saturate, so that's why also the errors are larger. If we compare this to the similar works from the Sonic project, or the other presented in the literature, we don't see that the environment plays any role in creation of brown dwarfs and low mass stars. So the IMF still is universal in our galaxy. One more thing that we did for now is actually the ratio of stars to brown dwarf. So that's a stars to brown dwarf ratio presented as a function of density of stellar surface density. I mark the regions with the OB stars. The width of the bar doesn't have any physical meanings. It's just to mark them on the plot. I mark the clusters that have OB stars but within the errors, the uncertainties of this plot, because how the plot has been created. If we have the ratio 2 to 5, it's 2 to 5, but if it's a value, then it's value plus 1 sigma around it. Within the uncertainties, all of that stays stable or have similar results. So to summarize and conclude, what we get for now is that we have the deepest and largest near-infrared survey for the RCW38. The IMF is in the segmental power law with respect numbers. Star to brown dwarf ratio is 2 to 4, a little bit on the upper side. So we find no clear evidence for the variation in the formation efficiency for the brown dwarfs due to the presence of OB stars or the change in the surface density. We still have few things we want to address before we make the work final and publish it, which is the effects of multiplicity and the mass segregation that seems to be present in the cluster, and also deal with the variable extinction to the membership assessment. And I think I'm done on time.
Thank you very much, Karolina. Yes, indeed, we have still plenty of time for discussion.
Right.
And yes, I would like to open the floor for questions. You can either raise your hand if you're on the Zoom. And we already do have a question from Tyler. Now just reminders of you to put the questions in the chat if you have them on YouTube. Thanks. Go, Tyler.
Thanks, Lucas. Thanks, Karolina. Nice talk. I'm Tyler Burke. I'm at SKA, actually. I just wanted to know, so if your results hold up in terms of you don't see any new evidence of any variation in the high mass regions, what might that tell us about brown dwarf formation?
So in the high mass region,
overall, actually, if there's no variation between the lower density and the higher density regions, what can that tell us about brown dwarf formation?
So in general, for me, it says that none of the scenarios plays is a dominant one. I think they are still mixing and they're very, very fairly. So all of the possibilities includes a little bit to the brown dwarfs population. Because if we would get a huge amount of brown dwarfs in RCW38, much steeper function, then it would be a hint that OB stars really play a crucial role here. But we don't see that, which does not exclude the way of forming brown dwarfs, but it just say it's not dominant factor here.
If I may, are you able to look in, say, a region like RCW38? Are you able to look at the brown dwarf fraction as a function of distance from, say, the O5 stars in the center?
Yeah, so that's what I'm saying. The mass segregation, how they distribute in that, we haven't investigated that yet. So that's mostly because we are not sure about membership, but it's definitely something worth to check.
Okay, I look forward to that. Thank you.
Thank you, Tyler. And I'd like to invite you to ask more questions either on the YouTube chat or on Zoom by raising your hand. And while I wait for that, I'll be happy to follow up on Tyler's question, actually. So basically what you're showing in your work now is that the IMF as a whole doesn't seem to vary with the region, right? But it's still possible that the local variations takes place on a very small scale, right? Or in mass segregation sense, right?
Yeah, that's still something that we want and we are trying to investigate right now. But the biggest question, the biggest problem for us is actually the extinction here, because it introduced yet another factor for the mass and the tracks and stuff like that. So unfortunately, we have to deal with that very carefully, and that's requires a lot of work for now, we are dealing with just the average extinction.
Yeah, I can imagine. So while I invite you to ask questions again, and I will be happy to follow up my question with another question while waiting for more. So indeed, so it seems like extinction is a big deal, but so what can we learn from observations at longer wavelengths, right? As for example, at sub-millimeter. There we're probably looking at much younger sources, right? But is there, is the evolution there present, or are there such works?
So I'm not familiar with any studies with the sub-millimeter range in RCW38, unfortunately. So I cannot say comment about the results. But definitely would be nice to see how it goes to the class 0 sources, how many of them we can see, and will the IMF still follow this regime?
Yeah, thanks. And we have a question from Dominika, please.
Hi, Karolina. Thank you for the great talk. You showed a really great data set from Hawkeye. And I'm curious, did you think about the follow-up studies with spectroscopic observation using integral field instruments?
Not yet. For now, I'm a little bit overwhelmed with finishing this project. But yes, definitely, we would like to get follow-up spectroscopy like we did for NGC 2244 and other clusters. So that would be the goal, because then we actually can confirm. Right now, we have the membership probability, so we more or less know how many sources can be members of the cluster, but we cannot say which of them.
Okay, thanks.
Yes, thank you, Dominika. And we still have time for 1 or 2 questions, so feel free to raise your hand or put a question on YouTube channel if you didn't have a chance yet. And in the meantime, so I would like to ask a more general question. So because for me, not very familiar with those studies of young brontos, this was a surprising result. I would naively expect or guess, if I would have to, that will be a difference in IMF depending on the region.
We expected that too. So we were also curious about that. Not maybe expected is too strong word, but we were also curious how does it look like. What we actually have to have in mind is that those are results with the huge errors, with the huge uncertainties. And if the uncertainties in IMF are large, in the mass beams are large, then of course you can fit plenty of functions within them. So the results stay stable within the observational errors. And of course, with the observation, we can start seeing some kind of differences in IMF, even locally.
Yeah, but it at least says that those differences are not very big, as one probably would expect. Yeah, okay. Thank you. And we have a question from Giacomo, please.
Yes, thank you very much. Really, first of all, congratulations, impressive database, really, really nice. Really looking. So, in fact, looking forward to see whether there is a local variation in the IMF. That would be really, really interesting to watch.
That's the next step we are working on to
exactly.
On some clustering.
But my question would be: so do you? It's always the difficulties of this region is to disentangle also between the spread that you see because of multiplicity, because of differential reddening, but also intrinsic real age spread that might be, especially so we might expect a certain degree of age spread when you have such a huge, massive, let's say, stuff from a region. So I was wondering, so did you, to assign masses, and did you use a single isochron, right? A single age isochron?
Yeah, 1 megayears isochron.
1 megayear isochron, exactly. But it might be, I don't know, it might be fascinating to consider the possibility that the region is represented better by different, ages. I don't know.
I'm not familiar with any kind of indicator that the region can be older than 1 megayear. I think there is no point of investigating 1 megayear versus half mega year isochrones.
Well, at this point, certainly no. Yeah, you're absolutely
exactly,
yes.
exactly. Yes, I think the multiplicity will play a bigger role than
much bigger role
in age. It may happen when we start dividing the region, because there are some hints of the subclustering in the region already within the region in the Hawkeye data. So we may then start to see something, but for now we haven't touched that yet.
Okay. Thank you very much.
Okay. Thank you, Giacomo, and thank you, Karolina, for the presentation and for answering the questions. And let me just remind you that you can always get in touch with Karolina. You can find her details, contact details on the Hypatia Colloquium webpage. And with that, I'll thank you again. And if you can stop sharing your screen. And Dominika, you can start sharing your screen, and I'll give you the floor.
Thank you, Łukasz. Hello, everyone. Yes, my name is Dominika, and I'm a student here in ESO, and it's my great pleasure to chair today's Hypatia Colloquium with Łukasz. Our second speaker is Noel Castro Segura. He is currently a PhD student at the University of Southampton in the UK. He obtained his bachelor's in physics and master's in instrumentation and observational astrophysics in the University of La Laguna in Spain. And during his research, he investigates the nature of accretion onto compact objects, the interaction between their outflows and local environments, as well as their evolution. In particular, he uses simultaneous multi-wavelength spectroscopic observations of binary stars to determine the driving mechanism of those outflows and to test our current theoretical knowledge. Today, he will talk about the Outflow Accretion Legacy Surveys and simultaneous panchromatic observations of the low-mass X-ray binary Swift J1858. Noel, whenever you're ready, the virtual floor is yours.
Hi, can you hear me now?
Yes, we can.
You see my screen?
Yes, I can see it.
Okay, thank you very much for the introduction. And now you see the full screen, I guess?
Yes, that's true.
Okay, now I'm taking over. Thank you very much. Okay, first, I have to say that I'm very pleased to have this opportunity of talking about my research in this series of seminars at ESO. And I'm going to present one of the main works of my PhD thesis, which I named the Outflow Legacy Accretion Surveys, which indeed is a series of works. And today I'm going to present the first batch of these campaigns. This work, I have to thank a lot of people who helped me to carry this work, and here I'm just listing a short list of them because which are the ones that helped me to obtain the observational data. So first, before going into the matter, I'm gonna do a very brief introduction, starting from accretion. So accretion is the natural process of which objects in the universe grows in mass. It plays an important role across all scales in the universe, ranging from galaxies down to planet formations. And this includes the stellar systems, which is the field I work. More precisely, I work in accreting compact binaries. So these systems goes into episodes of enhanced accretion in where the luminosity is increased several orders of magnitudes. With recurrence time scales from tens to hundreds of years and typical duration of hundreds of days, these systems are the perfect target to study the evolution of accretion in human time scales. If we go more into depth, the systems I work, they are called low-mass X-ray binaries, and they consist into a central compact object, which can be a neutron star or a black hole, which is with a binary companion, which is a low mass, typically a low mass star, which is filling its Roche log and is transferring material to the primary system, forming an accretion disk in where the material is slowly accreted into the compact object. So every single accreting object we see in the universe, we see evidence of outflows, and they come into flavors. They can come in forms of jets or winds. So while jets carries a lot of kinetic energies, with winds, on the other hand, can take a large amount of mass. In these plots I'm showing you in this system, the low mass X-ray binaries, we normally see an unresolved radio emission that when we follow it in time, we can see ejectas of blobs. On the other hand, winds in this system are traditionally seen in the X-rays in form of blue-shifted absorption of some elements. These outflows are important because they are the mean how the system interacts with the environment. Indeed, when this interaction happens, or when these outflows happens in dense enough environment, like this dense H-alpha regions I'm showing you here, they can produce strong shocks. So these shocks give us a very great opportunity to obtain an independent estimation of the outflow's properties, such as the kinetic power and the magnetic field. Over the course of an outburst, the low mass X-ray binaries has a very characteristic X-ray light curves. In this plot, I'm showing you in blue the soft X-rays and in red the harder X-rays. As we can see, during the course of the outburst, the source starts in the harder state and then it does a transition to a softer X-ray spectrum and goes back into a harder state. For this reason, astronomers in the field tend to represent the evolution of an outburst in an X-ray binary in what we call the hardness intensity diagram, in where the sources start from follow these hysteresis cycles, going into outbursts here, then transitioning and going back through this lower branch. So now we have that this, in the course of the outburst, there are two very characteristic spectral states which are characterized by the X-ray spectrum. During the quiescence and on the right and in the rise, the X-ray spectrum is mainly dominated by a hard power law. And this is associated with an optically thin, geometrically thick accretion flow in the inner region. When the source transitions to a soft state, the inner region is largely replaced by a optically thick, geometrically thin accretion disk, and the spectrum is rather dominated by a thermal component. Remarkably, these two spectral states produce two very distinct outflows. In the hardest state, we normally see very strong, steady, compact radio jets, while in the soft state, we see strong X-ray winds in systems with sufficiently high inclination. So there is a strong anti-correlation with these two different outflows, which is currently not well understood. The two main theories behind in this field says that if both of outflows can be magnetically driven. However, if that is the case, that would require a dramatic reconfiguration of the magnetic field when it does the state transition from hard to soft. On the other hand, the thermally driven winds gave us a natural explanation in this case, because if the central source hits the surface or the atmosphere of the accretion disk, it can reach the kinetic energy enough to escape the gravitational potential of the system. And the fact that we don't see this, but the fact that we don't see these thermally driven winds in the hard state can be just as a selection effect. For example, the gas can be over-ionized, so we don't see, it cannot observe. So they are very difficult to observe. This is the traditional picture of the outflows in the system, but in 2015, the famous black hole binary before 4 Cygni went into outburst. And then the magic happened. With this, I mean, we detected winds in the hard state for the very first time. So these winds, this has a huge implications because these winds are not X-ray winds. These winds happen in the optical, in the recombination lines. And for this to happen, it requires a very high density and low temperatures. And as I say, the implications are huge because hence they can take away a lot of mass from the disk, which can be, for example, the mass loss rate of the wind can be 100 times of the accreted mass accretion rate from the companion star. And in total, it can take away 10% of the total mass of the disk. As I said, this has a very strong implication, and it can regulate in regulating the outburst of the X-ray binary, but not only carrying away mass, but also adding an extra source of irradiation by reflection on the wind itself, as is required by the modeling of the X-ray light curves. So the current observational picture in the system is as follows. We have over the course of an outburst, we have in the hard state, we have strong radio jets along with very dense optical winds. While in the soft state, we have quite hot X-ray winds. So the question is, are they completely different type of outflows, or are these just different phases of the same outflow? And what we are seeing is a selection effect. Anyway, traditionally, the smoking gun signature for winds in general and for accretion disk winds lies in the UV region. As I'm showing you here, this accretion disk in the ultraviolet from an accreting white dwarf. And the reason why the ultraviolet is special to detect these signatures is because it has very strong resonant lines like this carbon 4, silicon 4, and nitrogen 5. Even more, this region lies in between the temperature of the required temperature between the optical required for the optical winds and for the X-ray winds observed. So if optical winds and X-ray winds are the same, we might expect to see UV winds in these systems. 31st October 2018, Swift reported the detection of a new galactic X-ray transient. Astronomers rapidly gather data across the whole electromagnetic spectrum, and as you can see in these plots, the source exhibited very rapidly variation across all wavebands, from X-rays to radio, including the optical. This kind of behavior have only been seen in the past in the famous black hole binary before 4 Cygni. Furthermore, when we look into the spectroscopy, we can see that we detected clear signatures of spectrum. However, when we stack the full, whole GTC observations in different epochs, we can see that in this 2D plot, a trial spectrum, that where the intensity is represented in color coded. So the blue means absorption. We can see how these winds are highly variable. Despite that strong detection, so this gave us the perfect opportunity to go for hunting and search for UV winds. And such we did. We write a DDT to the Hubble Space Telescope, which we luckily obtained. And this very rapidly escalated to a series of DDTs. We end up obtaining 4 10-meter class telescopes, 3 X-ray telescopes, and 3 radio telescopes, all of them aligned to obtain strictly simultaneous data of this source. In this plot, I'm showing you the evolution of the outbursts in X-rays. And as you can see, here is where our observation happened. It was not the most viable one, but despite that, when we look into the data, we can see that the source exhibited a spectacular variability across the whole electromagnetic spectrum, even reaching up to a factor of 10 in the phi UV, with this amplitude decreasing toward longer wavelengths. So here I'm showing you the X-ray, phi UV, optical, and near-infrared simultaneous light curves. The fact that we don't see any lag between the different signals down to scale up to a second, it is suggesting that this variability is driven mainly by the X-rays. However, when we look into the full near-infrared light curve, we can see that there are very, very strong non-thermal flares, which are rather odd, because they are not regular at all, and they not always have an X-ray counterpart as we would expect. But getting back to the topic of outflows or of winds, here I'm showing you again this plot of the 8 epochs of observation with the GTC, and in particular the epoch we observed, it was epoch 7. As you can see, in comparison with the other different epochs, the signatures of winds is not the strongest, but it seems to be there is a hint. When we look into more detail, we can see that the data is consistent with having these p-signy profiles in the helium-1 line, and not only in GTC, which was observing for the first section of the observation, but VLTX shooter, which was observing during the whole observation, also detected the same signature. So despite of not being the strongest wind ever seen in the source, when we look into the phi UV, we see that here, this at least carbon-4, that resonance line has a very strong absorption profile, which is a signature of an outflow. Not only that, but when we look into all the emission profiles, they are all redshifted, as we can see in this oxygen 5 line. That is not only for that, but for all the others, and all of them have a hint of blue-shifted absorption, including the recombination line helium-2, which lies in that section of the spectrum. So, as you can see, the spectrum is very rich, but I want to draw your attention to these 2 lines, nitrogen-5 and carbon-4. Because this spectrum is not only giving us information about the dynamics in the system, but it's also telling us about binary evolution. More precisely, this ratio of nitrogen-5 to carbon-4 is extremely big. Actually, it's an upper limit. It's a lower limit, indeed. So, and what it's telling us is that the material in the disk, which is coming from the donor star, it has a CNO enhancement process. And this is an indication that the companion star is a rather massive in terms for what is this, a low mass sensory vanity. So that means massive, more massive than the sun. So we went into, you might remember that I showed you this archival data in where the source is detected in PanStar. So we took all the archival data, we fit an SCD and determined the temperature and the luminosity of the star in quiescence. And what we obtain is in agreement with the ultraviolet spectroscopy. When we lie these estimations into the evolutionary tracks, we can see that the star is likely to be a subgiant with around 1.3 solar masses. But going back into the topic of the winds, so we not only observe for first time ultraviolet winds, signatures of winds in a low Maxwell binary simultaneously with optical recombination wind signatures, but few months before, in a previous campaign, high resolution spectroscopy in X-rays also exhibited the tentative detection of P Cygni profile in the X-rays. There is, we know even more about the source when it came after the second sun constraint. These gaps of data is because the source was behind the sun, basically, and when it came out of it, it came into what it is, the soft state. When we look into it, what we found is that the source shows very strong dips and eclipses, which is indicating a very high inclination of the system. Furthermore, it also exhibited thermonuclear runaway explosions in the surface. And the surface means that it is a neutron star. So when we take all of this data and we constrain all the spectrum of the accretion disk with all of this information, what we obtain is that the optical and UV spectral energy distribution is consistent with a source accreting close to the Eddington limit. So, which it looks like this. It's worth notice that the X-rays are about a factor of 10 below the expected value in this ACD, and this is suggesting that at the time of the observations, it was highly obscure, which is also in agreement with the flaring behavior it displayed. So to summarize, I presented the first results of this campaigns actually, and here I can go through these points. We talk about accretion disk winds, more precisely what we show the first detection of UV winds along with optical winds and tentative detection of X-ray winds in the hard state for the first time. This indicates that these winds are probably always present, as is required by the modeling of the X-ray of the light curves. And also that the different signatures are just different regions or phases of the same outflow. In addition, we talk about the nature of the accretor, which is a neutron star because it shows thermonuclear explosions in the surface. It's also a high inclination, which is accreting near to Eddington luminosity, as the spectral energy distribution tells us. Furthermore, we talk about, we show that ultraviolet spectroscopy is a really powerful tool to study evolution of this kind of system. Yeah, I'm gonna stop there. Yeah, there is more data. We are still analyzing it. Yeah, I'm overwhelmed, as you can guess. Thank you.
Thank you very much, Noel. I would like to invite our audience to ask questions, either by raising your hand or typing a question into the YouTube chat. While people are thinking, I will ask a question for myself. So you mentioned those odd flares in near-infrared light curve. Do you have possible explanation of them?
Yeah, let me put the slide. The non-thermal, this one. The non-thermal flares, you mean?
Yes, yes.
Yes, so, well, there are various explanations. This is not my expertise. Actually, Federico Vicentelli is the one working on it. This is ultra-fast photometry they do with Hawkeye. And normally when you have a type 1 X-ray burst, for example, you will see the reflection of basically what you see in here is reflection from an X-ray flare into a surface, probably the companion star sometimes. Yeah, but the odd thing in the system is like, well, those, if they are type 1 X-ray flares, they have a very characteristic shape, which is a very fast rise and a slow decline. But in this case, those are very, very different. Also, sometimes it can be the base of the jet that change very rapidly, and this is reflected in the accretion disk. So those are the two main scenarios for this. But as I said, there are different groups, including here at the University of Southampton, where they study these very fast variations. However, the odd here is that we don't see the X-ray counterpart in most of them.
Okay, thank you. As I see, people are still thinking, so I may ask very naive question. Do you know if any other similar sources was already observed, was already found?
Yeah, well, these guys, they are very spontaneous, let's say, and there have been a few more. Actually, we observed another one last Christmas, I think, with HST, and there are a few of them. They pop up like popcorns. Sometimes there is nothing, and sometimes there are a lot. Actually, when this observation happened, I think there were like 3 transients going off at the same time.
Okay, so they're not as rare.
Well, sometimes you have none in 1 year, but yeah. We can, our estimation is like that there could be maybe 2 or 3, 4 per year. Okay. From 0 to 4, let's say.
Okay, thank you. I see Giacomo has a question. Please, Giacomo, go ahead.
Yeah, no, very, 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 thank you very much. Really, these are always fascinating objects. I had just a curiosity, because maybe you mentioned, but I mean, is this particular object, do you see in a particular environment or is in the field?
Well, yes, actually, because we have estimation for the distance and everything. This particular region, which is in the southern sky, is in the coordinates +28, +29, and -8, close to the bullets. There is a lot of these objects, and this makes sense because it's a more dense region.
Exactly.
And you need something that went off a supernova, like a black hole or a neutron star.
So so it's not a cluster, let's say, in a more classical terminology, let's say. It's
yeah, well, in clusters, there is people who study them in cluster as well, and they are much more easy, even more easier to happen, because if you have a black hole or a neutron star wandering around, it can find more easily a star to start playing with it.
Yes, especially. But so you mentioned, the distance. What's the distance?
This is about 10 to 16 kiloparsec. Basically, it's in the other side of the galaxy, and that is this is the galactic. Well, here is the galactic center, more or less. So this is in the other side of the galaxy.
Okay.
Which is quite impressive that we can get something that far. It has to be a pretty nice hole in NH.
No, indeed. I thought it was okay. Great. Wow, very nice. Thank you. Thank you.
Yeah. Thank you. Dietrich, please go ahead.
Yeah, thank you very much. The main problem of any accretion process is to get rid of excess angular momentum. And do the various states through which this source goes tell you something about the rate at which angular momentum is dissipated?
Yeah, well, that is a very good question indeed. And actually, one thing that I haven't mentioned here, but the magnetically driven winds, CEPI, French group, they in their simulations, they cannot read of winds in the magnetic field, magnetically driven winds. And the importance of this is that they can take a lot of angular momentum with them. The other thing, the natural or the normal way that we explain the accretion to happen is also by frictions due to there's a weak magnetic field, so there are some frictions and the angular momentum is slowly transported outwards. That is the classic one, but also if winds are magnetic, they can take away a lot of angular momentum and they can enhance dramatically the accretion rate. I hope that answers the question.
Thank you.
Thank you. We already have a question in YouTube. Marianne Heide asks, and also comments that your results are very nice with the UV spectroscopy. She's curious, is this the only source that has UV spectra in outburst? And what kind of resolution do you need to get a decent result?
Okay, that's a good question as well. Actually, we are using, for the UV, we are using the lowest resolution in COS, in the 5UV spectroscope instrument for HST. Normally, the speeds we see, they are of the order of from few hundreds to few thousands of kilometers per second. Actually, let me pull this plot. So as you can see in this direction, the wind was about at least like 300. Of course, the better resolution you have, the better you will detect it. But yes, in terms of, actually, let me show this one as well. Here is also the speed scale. And you can see that also in the optical is about few thousand of kilometers per second. The deepest detection. But the thing is, you need quite a decent signal to noise because these are not very deep. They are like 5% depth in the optical and a bit more deep in the UV. We observe after this event, we observe, we are working on data for 2 or 3 more black holes that X-ray binaries, that we obtained during the course of my PhD in my group, and we are working with them. But they are, I think that the most problematic thing with these objects is low-max X-ray binary. They tend to be super obscure. And as you can guess, they are super difficult to be detectable in the UV. Actually, those are the counterpart. I mean, the UV is the best to detect winds, but because also it scatters very well the light, it will get very easily absorbed.
Yes, thank you very much. I don't see we have any other questions, so I would like to thank you and congratulate our speakers of today, Noel and Karolina. And now I will hand over to Giacomo to close today's session. Thank you.
Yes, just thank you, Dominika, thank you very much. So from me, thanks to all Noel and congratulations to Karolina and Noel for the excellent talk and the science, and thank you for everyone for attending thank you to Dominika and to Lucas for actually chairing the session. Now the next week we won't have the Hypatia because we will have the last event of the ESO Cosmic Duologue, and it will be about the accretion history of the galaxy. So with Amina and Anna Bonach and Amina Elmi. So please, and chaired by Marina Reikuba from ESO. So please attend the event again. We will be informing you, and then we will be back on the Hypatia on next month, so in June until July. So we conclude with the last 2 months of the Hypatia. With this, we can close the event. Thank you very much, everyone, for being with us. And thank you for attending the talk, and see you soon. Bye-bye.
Bye.
Bye.
Bye. Thank you.
Thank you. Bye.